Okay, we continue. We are going to have a look at this Nvidia extended GPU memory, the third type of system. We have discussed that this extended GPU memory from Nvidia can be enabled on Type 1 system and Type 2 system. Today, we need to move to Type 3 system. And the Type 3 system, if you look at this document, Nvidia is saying the third type of system is multi-node single GPU. That means what? That means two or more single node multi-socket system. I mean, this text in red is the original document. The original document is saying that this kind of EGM be enabled on the third type system is two or more single node multi-socket systems. But I think there is an error here because if we follow the original document, it doesn't switch into the situation. So I think the text should be two or more single node, single GPU systems. And this single node, single GPU system is the Type 1 system. So Type 1 system is the one that the EGM could be enabled, and the Type 2 is four times Type 1 system fully integrated. That's going to make a single node multi GPU system. For this case, for Grace Hopper, is going to be single node 4 GPUs. That's the system we have discussed in the previous part. For this third system, if I'm correct that there is an error here, if we can understand that the third type system is two or more single node, single GPU systems. That means you have two or more Type 1 systems. This is the third type system, and then everything could be explained. Because what? Because if you look at these NVL32 systems, you have two or more single node, single GPU systems, and basically this is the Type 1 system. So you have two or more Type 1 systems, and then you are going to have you have two or more Type 1 systems, and if you can use the Nvidia NVLink integration to connect all these 32 nodes, you are going to have this kind of NVL32. And this NVL32 is really what Nvidia means. So for the third type system, if we have this NVL32 system, because here, what the NVL domain is a kind of multi-node NVL domain. So NVL and this NVL32 with Grace Hopper is a kind of NVL system. For these kind of systems, you still have an NVL domain. For this particular case, we have look at this one. You have an NVL domain, and for this NVL domain, you have 32 GPUs. Okay, but different from the NVL domains we have discussed in the previous part. Here, the NVL domain starts to be crossing the nodes. So you have an NVL domain with 32 GPUs, but the 32 GPUs belong to 32 nodes. So your multi-node NVL domain is crossing 32 nodes. That's the meaning of multi-node NVL domain. Okay, so here the fact is that this EGM could be enabled on this kind of NVL32 systems. And that's okay also for the future NVL72 systems. Throughout these slides, I'm going to use NVL32 for the discussion, but the discussion could be applied to the NVL72 system with Blackwell. So with Grace Blackwell, sorry, Grace Blackwell. That be applied to Grace Blackwell. Okay, so the document from the Nvidia, from this document, I've got this drawing. Basically, it shows that the concept is that you have one node which is node 0, and you have another node which is node 1. You can have multiple nodes. Okay, for this NVL32 means you have 32 nodes. In the previous part, in the previous part, we have discussed that for the Type 2 systems, for a node with 4 superchips, the 4 superchips are going to share a global page table, but actually the global page table is a logical one. In reality, this page table is going to be, the page table is distributed onto all the CPUs and all the GPUs of the system, because the system will have 4 sockets. Each socket you have a grasshopper, so you have in total 4 CPUs and 4 GPUs. So logically, you have a global page table, but that page table is basically distributed onto different CPUs and GPUs. So, but here, this document is showing us the same concept that for all the GPUs, because here you have 32 GPUs, you have a global NVLink page table, and this global NVLink page table could be consulted by, let's say, GPU 0, and GPU 0 checks this page table, is going to find out this word address to physical address translation, and then this GPU is going to use this translation to reach the destination to get the data that it wants to get. So again, we have some kind of logical global page table, but it's called NVLink page table. But actually, where does this NVLink page table exist? Is that within a node? Is that within a network switch? No, it's not like that. This NVLink page table is a logical one. Actually, this logical page table is made up of 32, let's say 32 page tables from all the GPUs belonging to this NVLink domain. So let's move on. Okay, we keep this one. We still have this NVLink page table. This is the NVLink page table. It's shared between all the nodes. So we are showing here, we have the first node, and we have the second node. These 2 nodes are sharing this NVLink page table. But, well, this NVLink page table, what's this NVLink page table? I've got this drawing from the Nvidia website. Okay, basically, what we have is that if the GPU is the GPU A is the exporter, means that the GPU A will have part of its memory be read by another GPU from another node. Okay, so you have another GPU B, which is the importer. So what we want to do is that we want to have GPU B access the GPU A's memory. But remember here, this node 1, this node 2, and this node 3 are all one node. For example, is one node of the NVL32 systems. So this is the NVL system, multi-node NVL domain. So if you have 32 GPUs, you have an NVL32 domain, but each GPU belongs an node. That means you have multiple nodes. So you have multiple nodes here. You have node 1, you have node 2, you have node 3, and each node is running its own operating system. You have operating system instance 1, operating system instance 2, and operating system instance 3. Each node is running its own operating system. This is totally different from the type 2 system. The type 2 system, on which we can enable this EGM is that you have 4 superchips, but the 4 superchips belongs to a single node. And on that single node, you have only one operating instance. And that operating instance is managing the whole system, including the 4 superchips. But here, for our example, you have 3 superchips. This is suppose is this node is a superchip. Each superchip has its own operating system. So here, what has been shown here are only page tables. You have a page table for node 2. You have a page table for node 1. You have 3 page tables. Basically, the text is saying GPU page tables are controlled by GPU B and C process. That's true. That's normal. Each GPU need to control their own page table. That's okay. And here is saying that for node 1, the GPU A is physical memory is page tables for fabric address space controlled by GPU A. Okay. We need to spend time just to think about that. Now, in the for GPU, normally GPU is going to have its own page table to do the virtual address to physical address translation. Okay, and for the type 2 system, sometimes you are going to have got this translation which points to not its own physical memory. It could be pointing to a physical memory from another superchip. Okay, maybe it's a good idea to come back this one. Here is that this GPU, it has its own page table. Okay, and then this page table could point to its own HBM memory. Okay, and this page table could point to a remote memory. It could point to this memory. Okay, so then when this GPU tries to read the memory, when it tries to read local memory, it uses this page table to get the physical address and then use that physical address to read the data from that physical address. When the page table points to a remote physical memory, the GPU is going to use this remote physical memory to get data. I mean, this this memory access will be going through this NVLink C2C and reach another GPU and use that physical address to get data. But anyway, it's going through this NVLink C2C link, but it's always using this physical address. So it could be pointed to its own physical address, or it could be pointed to another GPU's the physical address. But the difference here is that for this is a node is just with only one operating system. These 4 nodes belongs to this single nodes is managed by this operating system. So it's natural for this GPU to access the other superchips physical memory because the memory has been unified and it has been unified and it has been addressed. It could be addressed globally by each CPU and the GPU. Now, this was the situation with EGM for Type 2 system, but the big difference for this kind of system is that right now the nodes are with its own operating system. So this GPU now for the previous for the Type 2 system, the node A and node B are interconnected by the NVLink C2C. By NVLink C2C, so the virtual address, the page table could point to the physical memory of another node. But for our particular case, right now, it's no more. It's not anymore. It's not possible anymore. Because what? Because right now you have 2 operating systems. You have this operating system and the second operating system. In this case, there is no possibility for this GPU page table to have its virtual address pointed to another node's physical address, because here we have 2 OS domains, we have 2 independent physical memory physical memory domains. Let's see it this way, because here this physical memory domain can only be accessed by GPU B, and this can only be accessed by GPU A, and this kind of reference is no more possible. So for this kind of system to work, for this GPU to export its memory to be read and write by another node, the reference can only be done by going through this fabric address page table. Okay, this is no more. It's not for this one. Okay, so maybe we need to remove this stuff. Okay, so it's no more possible. So right now, if the GPU A wants to export its memory to be read and read by GPU B, then in the case that the GPU B wants to read the memory of GPU A, there is only one possibility, is that you have this fabric address space. You have another page table for this fabric address space. So you have another page table here. And then you can, in GPU-B's page table, you can have an an entry for this, for its virtual address. You have this virtual address. You are going to have a mapping from virtual address to fabric address. And this fabric address will be mapped to this one. This is the page table for fabric address. If you have this fabric address, you can look up from this page table and find out this physical address. And this physical address is the one which is holding the data that the GPU-B wants to read. This is physical address. This is fabric address. And then the GPU can read the data from another GPU's memory. This one here, we have this drawing is showing this square as a page table or as two page tables. Here is the same thing. You have one page table. You have one page table. You should have another page table. You have one page table. You have another page table. You have one page table for the virtual address space. This one. You have another table for the fabric address space. Here we come back to this one. Here, from the document from Nvidia, is showing for this kind of NVLink 32 systems. They'll have an NVLink page table, but what I'm saying is that there isn't an NVLink page table globally exists somewhere within a node or within the network. It doesn't exist. This is a logical object. Logical and object. It doesn't exist in reality. In reality, what exists? What the things we have in the reality is this page table for fabric address space. You have this page table for fabric address from GPU A. You have another one from GPU B. You have another one from GPU C. Okay. In other words, you have a page table for the fabric address space from node 1, from node 2, from node 3. Globally, all these page tables belong to all these different nodes. Globally, these distributed page tables, you can think this is the NVLink page table. Okay, you can think the sum of all these page table for fabric addresses from all the nodes. You put everything, you put all of them together. The sum of all these small page tables, this is the logical NVLink page table. So again, NVLink page table is a concept to describe the idea. So this is a kind of a logical object. It doesn't exist physically somewhere. So this logical, if you have to think there is an NVLink logical page table, that's going to make things easier conceptually. Then you think, okay, this logical NVLink page table physically is distributed onto the nodes belonging to this NVLink 32 NVLink domains. And here, this exactly what has been shown by this pick drawings from the Nvidia documents. Okay, so to read data from a remote node. So what we need to have, this virtual address to fabric address translation, and then we need to have this fabric to physical address translation, and then after you have done these two translations, the first, the second, and then you can have the possibility to read data. So this this fabric address is used to pass through the network. Here is saying that we spent to have a look for this one. Is saying that the fabric address is unique in the fabric, because each GPU is going to be connected to the fabric, and each GPU is going to have a unique fabric address, and the fabric address for the GPU is allocated by the fabric manager, and this fabric address space is global for the GPUs. So the page table is with this fabric address, and this fabric address is addressable globally. I mean, all the nodes could use the I mean, all the nodes, all the important nodes could address this page table and refer to this by using the fabric address and to reach this fabric page table for the fabric address space. Okay. I know it's not so easy to understand. So what I have done is that I have drawn the page table and the steps for the remote memory access in a single drawing. So maybe we just need to think about that. We need to go through that, and things is going to be clear. What we are talking about here is we are talking about multi-node memory sharing, and that this is targeting this kind of NVL32 or NVL72 systems. We are talking about memory sharing between nodes. Here you have node 2, you have node 3. By definition, each node is the related hardware plus the operating system instance, which is running on top of it. So you have this operating system instance 2, and you have this operating system instance 3, and you have operating system instance 1. Okay, we have 3 nodes. We have 3 operating systems. The 3 nodes are interconnected by the NVLink network switch. And because we 3 nodes have been shown here, but is for the discussion we are targeting NVL32. Basically, here we could have a maximum 32 nodes if we are talking about NVL32, and if we are targeting NVL72, it means that this NVLink network could connect up to 72 nodes. Okay, depends on the size of this NVLink domain, but 3 nodes are enough for us to explain the things clearly. Okay, this is the page table of node 2 of this GPU. This GPU is GPU-B, and this one is GPU-C. C. And this is the page table for GPU C. And here you have the page table for GPU A. For GPU A. And everything in this square is the page table. Or you have one, or you could have page tables. One is for the fabric address space, the other one is for the virtual address space. You have two page tables. I think this is, I think in the real life, it's easier to have two page tables. One is for virtual address space, the other one is for the fabric address space. I don't know the implementation details, but I think the best case is you have two separate page tables. I think that's going to make things easier, but this depends on the implementation. If somebody somehow they have decided to merge this one, that's their choice. But I think it's better to keep it separated. So we can think that each node we have two page tables, and the sum of this fabric address space page table of all these nodes. Oh, sorry, this one, and this one, and collectively, we can understand, we can think that collectively this fabric address space page table works as an logical global NVLink page table, but it is distributed. Okay, anyway, let's have a look how a node is going to read to another node's memory. Okay, this is the exporter. The importer is the GPU who needs to read to another GPU's memory, or in other words, the importer is the node or the GPU who needs to read to another node or GPU's memory. Okay, so at some point, let's see this GPU, it needs to read, it needs to access to this memory. There are some data here that GPU B need to read from GPU A. This is GPU. GPU B needs to read data from GPU A. So then the first step is that the GPU needs to read the data. The first thing it's going to do is that the GPU A, the GPU B here is going to look after the virtual address from its virtual address space. Okay, so it knows that it needs to access the data stored in this virtual address space. And this is the page table. It uses this virtual address as the index, and it is going to find out this entry from this page table. If the data that this GPU wants to read is from its own memory, things are going to be very simple, because in that case, we are going to have the entry of this page table. This entry points to a local physical memory. So here you are going to have something like a physical memory, physical memory address, and it points to some. It points to a physical address, and in that physical address, the data is the data that this GPU wants to read. This is the case if it's reading locally the data, and then things is going to be very simple with this physical address. The GPU is going to just read the data. Okay. Now, the things for now is that you are not trying to you are trying to read to an remote GPU's memory. So here this doesn't work. It doesn't work this way. Okay. So the GPU knows the virtual address it needs to read the data from. And then the GPU memory management unit is going to look after this page table to find this entry. I mean, this is the page table. Actually, this is the zoom in of this page table. We need to understand this page table is a piece of data stored in the GPU's memory. Most of the time, it's a kind of high-speed memory. Is a piece of data stored inside this GPU. It has been zoomed in to make things clear. It has been zoomed in. Okay. And then this GPU MMU, memory management unit, is going to look for the mapping from the virtual address. Now, because this GPU, this streaming multiprocessor is going to use this virtual address to find they are going to try to use this virtual address to read the data from. And then the GPU MMU is going to consult this page table, try to find out where is the data located. Okay. In the case the data is located in another GPU's memory, in another node's memory, what you are going to have is that you have a fabric address stored here. The mapping is going to be from a virtual address to fabric address. You have an entry here. The entry is the fabric address. And then the result will be back to the GPU memory management unit. The memory management unit is going to find out, oh, okay, so this virtual address is pointed to a fabric address. It's not pointed to a local memory address, so it's a fabric address. In the case that's a fabric address, I have to ask the network to help me. So this GPU is going to send the request. The request is to get data from this fabric address. The request will be sent into the network. Okay. The request is, for sure, the request is going to be the type of the request could be read or write, and the address to read or to write is the fabric address. So this fabric address will be sent into this NVLink network. With this fabric address, the NVLink network has the possibility to route this request to the destination GPU. Now, the request has been sent to this destination, and with this fabric address. It has been sent to the destination GPU. Okay. Now the GPU receives this data request from GPU B. This is GPU A. It received the request from GPU B, and within the request, it will find out that there is a fabric request, a fabric address. Then the GPU is going to look after is translation look-aside buffer. You can just think that this buffer is high-speed cache, and within this cache, we have this FA to physical address translation. Okay. Within this buffer, we can understand that we have this page table. This page table is stored within this buffer, this translation buffer. So this unit, okay, this is is marked here. New Hopper NIC functions ensure request is legal and maps to GPU physical address space. So here, this is the NIC function, and this NIC function is going to check this TLB buffer, and within this TLB buffer, basically you have this page table. But I'll put this page table here, and I'll show and zoom in of this page table. So here that this NIC function is going to check this page table. Okay. And by referring to this page table, because here we have this, we are going to, the GPU is going to use the fabric address as the index and try to find out what's the entry for this fabric address. And what is going to find out is a physical address is going to find out we have a physical address here. Okay, so it has consulted this page table, and it has found out that for this fabric address to get the data, all this GPU needs to do is to read data from the physical address that has been stored in this page table, in this entry referred by this fabric address. So then the GPU is going to know, okay, now understand that what this GPU needs to do is just to use this physical address and read the data from this physical address. If this physical address points to this data, and then the GPU just needs to read this data and send it back through the network to GPU B. And this is the process for GPU B to read the memory of GPU A. Okay, here we have a GPU, we have a node. A GPU is within the node with operating system. This is the page table. The page table is a piece of data. It's a piece of data. It's a kind of lookup table, and this table usually is associated with a kind of memory. Usually is kind of memory such like cache. It's high-speed, high bandwidth memory to make the translation more efficient. And between this page tables. Everybody is managing its own page table. If this node 2 is going to export its memory to other nodes, the same thing is going to happen. Its fabric address is going to be filled in, and this physical address is also going to be filled in. So this is how the things happen under the hood. I just want to point out between this page table and this page table, you have a kind of a link as dash line. This link only means the fabric address is pointed here. This fabric address stored here, the address points to this address space. This is a fabric address. This fabric points to this address. There is no other relations except they are the same address. That's the only relationship between the two entries. Between the two entries, the only relationship is the fabric address stored in this page table refers to the to one fabric address, which is in the address space, in this fabric address space. There is no other relationship between the two. This line, this line in color blue and this line in color green, these are the links. These are the physical links that the data and the request will be sent on top of them. The request and the data will be transferred from a GPU to network, from network to the GPU. This is the line stands for the real links, the real physical links. Okay, I hope I have made this multi-node memory sharing clear. But I'm not 100% sure. There is another page we need to go through. This is going to help you to understand. Basically, this drawing is the same as this one. It's here, but here. To illustrate that the relationship between the page tables, between the page tables, the relationship between the GPU, and where is this page table located. I have put these two drawings. I have put them together, but this is just try to make things easier to understand. But here we need to have a final look of this network for multi-node memory sharing. So the network for multi-node memory sharing is the NVLink network. Finally, this network is for peer-to-peer memory access, and this is the famous NVLink network. So we need to have a look at this NVLink network. We have gone through the drawing in the previous slide, but here, what I want to point out is that here you have the source GPU, which is GPU is also called importer, which is the GPU which is going to read or write to remote GPU memory. So this is the importer, but this GPU is sorry, the drawing is not beautiful. Okay, so this GPU is within a node with one operating system instance. Okay, and again, the other side, we have another GPU, and this GPU, it belongs to another node with its own operating system instance. We have a totally different two nodes. Each node has its own physical address space, but the two nodes, they share the same fabric address space. So here we need to have a look at these key differences between this NVLink network and the NVLink C2C. NVLink C2C is linked within a superchip, or is also the link within the Type 2 systems with this kind of EGM, with this kind of extended GPU memory enabled. That's for these systems. But up to now, the NVLink C2C is only for connecting two GPUs, one GPU with one CPU, or connecting two CPUs. Everything connected by the NVLink C2C belong to the same node. So everything connected by this. So this NVLink C2C is a kind of a intra-node connection. Everything connected by this NVLink C2C is within a node. That means everything connected by the NVLink C2C has one address space, one shared address space. Everything connected by the NVLink C2C, they have one shared address space. And by this NVLink C2C, if you request, the addressing of the request is physical address. And the collection setup of this kind of C2C is during the system boot. And it is going to be always there until the next boot. And it's not isolated. Okay, we have a look at this NVLink network. The NVLink network connects the NVLink network connects multiple nodes, and these multiple nodes, each node has its own independent address space. So each node has its own independent address space. Each node has its own network address. So the reference to the memory, to the remote memory, cannot be done by the physical address, because the physical address, we have different physical address space for this node, for left-hand side node, and for right-hand side node. We have different physical address space. We cannot use the physical address space from left-hand side to refer to a data stored in the right-hand side, because the two different address space are totally independent. We cannot do that. And to refer to the remote GPU's memory, you have to go through this NVLink network. You have to go through this fabric address. So this is the link between the two GPUs, between the two nodes, between the two systems. And then the setup, the connection setup between two GPUs going through this NVLink network switch is the setup will be done at the runtime API call by software. So the the connection will be set up by software when you have this kind of API call. And after the call has been done, this kind of connection will be removed, will be destroyed. And the isolation, yes, this is isolated. I mean, the two GPUs, the physical address. I mean, that's two systems, so they are totally separated. Okay, so this is up to now. What we are talking about is how it works, how this kind of GPU, how this multi-node memory sharing. How this multi-node memory sharing works between the nodes, how it works between the nodes. This is something under the hood. But from the programmer's point of view, from the user's point of view, they program the system to have this system function correctly. So the programmer to make this system works, to have this multi-node memory sharing, there are the coding that has to be done by the programmer. And here it has summarized pretty much the steps for this kind of coding to be done. Okay, so here we are going to go through this text very quickly to understand what's the rough process. What are the steps to have this coding done? So we have CUDA processes that are running on each compute node in its own OS domain. So right-hand side, left-hand side, we have at least we can have two CUDA processes, one on each node, running on the system, on the node within its own OS domain. Okay, so on one node, on the exporter, on one node, on one node actually is on the exporter. On the exporter, and here we know this is the exporter. On the exporter, the CUDA process allocates GPU memory and obtains the corresponding shareable memory handle. This allocation and handle creation trigger the establishment of virtual address to physical address to fabric address mapping on the exporting node. On this node, we are going to have an entry for the page table with this mapping of VA virtual address. So this is virtual address to fabric address to physical address. You are going to have a kind of mapping set up in the page table. And then for importing, for the importer to import this memory, the exporter process, shares the memory handle with the coordinating process on other nodes using MPI or equal. So we are going to find out that here later on in the document is saying that this share will be done by TCP/IP. Okay, but actually, for sure, it could be shared by this MPI. So this is the inconsistency from the documents of Nvidia. here is mentioning MPI NICO, and in the following documents, it's mentioning TCP/IP. But from my point of view, these two kind of network, these two kind of protocol will do the job. It's okay for both. And on on these nodes, I mean on the importer nodes, the CUDA process prompts the GPU driver to import the relevant memory using the received handle. Okay, and then on the importer side, the GPU driver on the importing node, okay, creates the requisite memory objects and establish the VA to FA mapping. Okay, so this is to set up the multi-node memory sharing scheme. After this has been set up, after the page table has been filled in, after all this has been done, then when the exporting process means the importer, when the importer tries to access the virtual address space, the GPU memory system on the importing nodes recognize the corresponding physical page table by leveraging a foreign GPU and that generates the NVLink package to access the pertinent memory. Okay, this is the steps that the programmer has to follow to program these kind of systems using the multi-node memory sharing. Okay, I think it's not. I think right now, if we just read these documents, it's not so clear. What we need to do is that we need to have a look of a piece of data which is going to use this multi-node memory sharing system. So this code is going to show us how the programmer is going to program these systems to make it work. So we are going to continue in the next part. Let's just have a rest of 5 minutes.